Hello and welcome to this Revision Monkey video on what's going to be in the 2022 exams. This is for the AQA specification and it's for Separate Physics, sometimes known as Triple Science in some schools. So this video focuses on the content for Physics Paper 2 and is for higher tier students. First of all, let's look at the topics that won't be assessed in this paper, and these are moments, levers and gears, electromagnetic waves, black body radiation, and permanent and induced magnetism, magnetic forces and fields. They have told you they require practical to focus on, and that is the separate only reflection and refraction practical. I've put a link for this in the description, so do have a look at this video so you can focus on the content that you need just for this required practical. And they've also told us the topics of major focus for the exam, and these are forces and their interactions, work done and energy transfer, forces and elasticity, pressure and pressure differences in fluids, describing motion along a line, momentum, waves in air, fluids and solids, solar system, stability of orbital motion and satellites, and Redshift. So these will be the major focus of this video, and also keep a lookout in the description because I'll put a link there for some practice questions on these topics as well. Let's first look at the difference between scalar and vector quantities. Some examples of scalar quantities are speed, distance and time. And some examples of vector quantities are velocity, displacement, force, acceleration, and momentum. Now, the difference between the two is that scalar quantities have magnitude only. So magnitude is size. So you can give one of these quantities a big value or a small value, and that will be changing their size. So, for example, a speed of somebody could be 5 meters per second. That's giving the size of the speed or the magnitude. Somebody could walk a distance of 10 meters, for example, and that's the size that you give it. Whereas a vector quantity has both magnitude, so the size, and direction. Velocity is the vector quantity which is related to speed. So you'd give, rather than just giving a size like 5 meters per second, you'd also give some indication of direction. So you could say to the right, or in physics, sometimes you'll see that they'll put a plus or a minus in front of the velocity as they've given a plus or minus to a certain direction. So if they've decided that everything moving to the right is a plus and everything moving to the left is a minus, they can put that plus or minus in front to indicate the velocity. Displacement is the vector version of distance, and you'll also have force, acceleration and momentum that are examples of vectors as well. So moving on to forces then, we said it's a vector, so we can use arrows to show both the size of the force and the direction of the force as well. So for example, with this falling tennis ball, it will have air resistance going upwards, represented by this arrow, and weight acting downwards, represented by this arrow. The direction of the arrow shows the direction of the force, and the size of the arrow shows the magnitude of the force. So we can group forces into contact and non-contact forces. So some contact forces include friction, air resistance, tension, and the normal contact force. And in these cases, all the objects have to be touching. So friction is when two objects are rubbed together. Air resistance, you've got the air particles colliding into an object. Tension, you'll experience that when you pull two different ends of material like a rope. And a normal contact force is a contact which is acting at the normal, which is at 90 degrees to the object, which is touching another object. So for example, a book on a table would experience a normal contact force at 90 degrees from the table. Some non-contact forces include gravitational force, electrostatic force, and magnetic force. And in all these cases, the objects are separated and don't have to be touching in order to experience the force. Some forces can be measured using a Newton meter, and forces are measured in newtons. So this is a Newton meter. You could, for example, hang your object on the end of this hook here, and that will let you know the weight of the object in newtons, or you could use this Newton meter to pull or push an object and measure forces in that way. Let's have a look at this example. We've got a diver diving off the diving board, and we've got a gravitational force pulling that diver down towards Earth, or we can actually call this weight, because weight is equal to mass multiplied by gravitational field strength. Weight is a force, and it's measured therefore in newtons. Mass is measured in kilograms, so if you ever see it in grams, you would have to convert it to kilograms by dividing by 1,000. And gravitational field strength is measured in newtons per kilogram. The weight acts at a single point known as the centre of mass of an object. So here, for example, in this person, this could be the centre of mass of that person. It's quite difficult to work out for irregular shaped objects where the centre of mass is, but that's where the weight will be acting downwards. On Earth, the gravitational field strength is 9.8 newtons per kilogram, sometimes round up to 10. What is the weight of the diver if he has a mass of 50 kilograms? Well, weight is mass times gravitational field strength. So if we do the mass times by 9.8, we'll get a weight of 490 newtons. Let's look at an example if this diver was on the moon. On the moon, the gravitational field strength is just 1.6 newtons per kilogram. What is the weight of the diver if he has a mass of 50 kilograms? Well, importantly, the mass does not change. Mass is still 50 kilograms, but if we multiply it by 1.6, the diver would have a weight much less of just 80 newtons. So the key thing is your mass, wherever you are, does not change. However, your weight, because in physics weight is a force, we're not talking about mass in kilograms. When we're talking about weight in physics, we're talking about a force in newtons. So really it's important to say that your mass is, you're talking about your mass when you step onto some scales rather than your weight, because in physics weight is the force with which you're pulled towards an object. So that's why on the moon your steps will be a lot lighter and a lot bouncier, because there's less of a gravitational field strength pulling you towards the moon compared to the Earth. So important, mass stays the same wherever you are, but your weight can change depending on the gravitational field strength of the planet you are on. Looking at resultant force, then you can think of the resultant force as the overall force acting on an object. So when you take into account lots of different forces, what's the overall force? So if we look at this block here, we have 5 newtons pulling to the right and 2 newtons pulling to the left. So the 2 newtons pulling to the left, we need to take away from the 5 newtons on the right, and we would have an overall force of 3 newtons. And because force is a vector, we'd have to tell the examiner the direction that that box will move in as well. Because there's more newtons pulling it to the right, overall it would be pulled to the right. You might also get an example where there's multiple forces acting on an object. For example, if it's still 5 newtons pulling to the right, but in this case we've got 2 newtons and 3 newtons to the left. Overall on this side there'll be 5 newtons pulling it to the left and 5 newtons to the right. So 5 minus 5 would be 0 newtons. So when there's 0 newtons, there is no resultant force, or it's better to say no overall force, and the resultant force is 0. There's a little bit extra for higher tier students where you might be asked to complete a free body diagram, which is a diagram which represents an object and the forces acting on that object. So this question says complete the free body diagram to represent a ball with a resultant force of 10 newtons downwards. Well, at the moment it's got 5 newtons up. So if we want a resultant force of 10 newtons down, then we must have 15 newtons acting downwards, because overall now we'd have 15 minus 5, giving a resultant force of 10 newtons downwards. And this could well be a scale diagram where you'd have to really accurately draw the arrow in an exam. The second question says complete the free body diagram to represent a ball with a resultant force of 0. So this is just checking your understanding. If there's 5 newtons upwards, to get a resultant force of 0, there must be a 5 newtons force downwards. A little bit more tricky work on forces for higher tier students is resolving forces. This question says resolve the force into its horizontal and vertical component. And what this is saying is if this force is acting at an angle, we can break up that force into the horizontal component of that force and the vertical component of that force. So this is an example of what you might need to do. You would draw the force on a graph paper that they would give you in the exam. So draw the arrow to the correct size and scale. They might even put this one on there for you already drawn if you don't have to copy it from a diagram down there. You'd have this arrow and you would need to measure this arrow to calculate your scale. So if we measured it and it was, for example, 8 centimetres, we could look at our scale. So we'd have 5 newtons for every 8 centimetres. And if we divide both sides by 8, that will make this 1 centimetre, because 8 divided by 8 is 1, and that will make this 0.625 newtons. So now you've got your scale, you know that every 1 centimetre equates to 0.625 newtons. You can then draw an accurate horizontal line along the bottom, measure the length of this line, for example 7.5 centimetres, and use the scale to calculate the force. So we multiply each centimetre by 0.625. So 7.5 times 0.625 would give you a force of 4.69 newtons. And vertically, we again would draw a straight line to the top of this force, measure it with a ruler, and then use our scale to calculate the vertical force. So that's taking a force at an angle, resolving the forces into the vertical and horizontal components of that force. And what this is basically saying is, yes, we've got this force at an angle, and this would be like pulling this object here with an upwards force of 1.75 and a sideways force of 4.69 newtons, and that would result in the object moving in this direction with a force of 5 newtons. You could also have a scenario where they ask you to calculate the resultant force when these forces are at angles, so it's not as straightforward as writing a force going to the right and a force going to the left. What you'd need to do is you need to redraw the force arrows, but draw them end to end this time. So if we start off with this one, and at the end of this one we are going to draw the next arrow like so. This gap here is going to give us the size and the direction of the resultant force. So you'd measure it from this point, because this is where we started, up, and you would draw an arrow connecting to that second force that you've put on. So just neaten that up here for you. This arrow here would represent the resultant force, and try and be really accurate, more accurate than I have, to make sure your arrow starts here and meets at the tip of that arrow. You could then be asked to work out the direction of that resultant force. So if we put this vertical line here, you could measure the angle relating to 0 and 180 down here. You could measure that angle using a protractor. That's why you're asked to bring a protractor in the exam. And you could be asked to measure that, for example. So that could be around 40-ish degrees, but you'd need to do it accurately. And you could also be asked to use a scale diagram to calculate the size of that force. So they'd have to give you some values here in order to measure the scale diagram. For example, if they told you that was 5 newtons, you could measure that line in centimetres and work out what each centimetre would be worth in newtons, and then calculate the size of that force. A final example is if you see a situation where the forces are in equilibrium. When forces are in equilibrium, there is no resultant force. So again, you draw the arrows end to end in any order. So let's look at one scenario. You could draw this one here first, and then on the end of it, this one here, and then on the end of it, this one here. And what you'll notice is they form a complete shape without any gaps. And in that case, that's telling you that the object is in equilibrium and there is no resultant force. Doesn't matter what order we put these arrows in. We could start with the longest one first, and then this one, and then this one. If they complete that complete shape with no gaps, then there is no resultant force and the object is in equilibrium. So we'd say the resultant force in this case is 0. Work done and energy transfer. When a force causes an object to move through a distance, work is done on the object. So because we're talking about distances, we can say a force does work on an object when the force causes a displacement of the object, because distance and displacement are linked. Distance is scalar and displacement is vector. So there's an equation that links work done, force and distance, and this is work done equals force times distance, where work done is measured in joules, force is measured in newtons, and distance is measured in meters. The reason why work done is measured in joules is because it's the same as energy transferred, and obviously energy is measured in joules. But you do also need to be aware of another unit for work done, and that is Newton meters. So 1 Newton meter is equal to 1 joule. And the Newton meter comes from the fact that you're multiplying a force measured in newtons by a distance measured in meters. So you might see work done in Newton meters, or you might see it in joules. So an example using the calculation calculates the work done when 20 newtons of force pushes a wooden block 25 centimetres. So the first thing we need to do is sort out these units, because we said distance needs to be in metres. So convert this to metres first of all. 25 centimetres is equal to 0.25 metres. And then put our numbers in the calculation. Work done equals the force multiplied by the distance, which would equal to 5 joules. Or, like we said in the exam, you might see it as 5 Newton meters. In this topic, we need to distinguish between scalar and vector quantities. And the two we're going to focus on are speed and velocity. So the scalar quantity speed has magnitude only, which means it only comes with a size, whereas velocity is classed as a vector because velocity tells you both the size and direction of movement. So for example, with speed, if an object was moving to the right at 3 meters per second, we would just class the speed of the object as 3 meters per second. However, with velocity, we need to indicate the direction that the object is moving in. So what they do in physics is they state which direction is positive and which direction is negative. So, for example, a scientist could say, right, let's say that everything moving right is positive and everything moving left is negative. So rather than just writing 3 meters per second, if an object was moving to the right, when we talk about velocity, we'd have to be talking about plus 3 meters per second. So this here just indicates the direction that the object's moving in, hence taking into account direction as well as size. If the object was moving in the opposite direction, then at that same speed, we would then be saying it would be minus 3 meters per second to show it's moving in the opposite direction. So they are both very similar things. They're to do with how quickly an object moves. However, speed just takes into account the size, whereas velocity takes into account direction as well. And then there's another pairing to look at, which are distance and displacement. Displacement is the vector version of distance. Let's have a look at an example. If we have a starting point and an object moves 5 meters and then another 5 meters, the total distance would be 10 meters, 5 plus 5 making 10. However, if we look at the same scenario with displacement, with an object moving 5 meters and moving another 5 meters, because it's returning back to the same original starting point, we would actually say that there was a displacement of 0 meters because they've gone up and come back to this same starting position. So therefore its displacement is 0. So that's the difference between the scalar and vector quantities, speed versus velocity, and distance versus displacement. You need to learn some typical speeds off by heart, so I suggest writing these down, having them on some revision cards to learn them. And these are walking, 1.5 meters per second, running, 3 meters per second, cycling, 6 meters per second. So if you remember walking, running, cycling, each time these are doubling up. These are typical speeds. And then you also need to know for some other modes of transport, which is a car, 25 meters per second, a train, 30 meters per second, and an aeroplane, 250 meters per second. So when they talk about a scenario, for example, a car travelling, and they want you to do some mathematics with that, they might ask you to estimate something about the motion of that car, and if they do, and they haven't given you a speed, then you should be using this typical speed for a car. And the same if they talk about an instant involving, for example, the momentum of a cyclist, and they're talking about estimating momentum. Well, think that the typical speed of cycling is 6 meters per second. So these are just some facts to remember. A couple of other little facts then. Firstly, that the speed of sound is 330 meters per second. And also they just want you to have an understanding that the speed of wind varies. Okay, so sometimes it might be really fast wind, sometimes it would be really slow wind, as you probably know, but that's just one thing that they might ask you to apply your understanding of in the exam. Let's look at some speed equations then. This question says a bee flies at a speed of 10 meters per second for 40 seconds. How far does it travel? So this is applying the equation distance travelled equals speed times time. Distance travelled is measured in meters, speed is measured in meters per second, and time is measured in seconds. So for us to calculate this, we would do 10 times 40, which would give us 400 meters. A little something for higher tier then. Motion in a circle involves constant speed but changing velocity. This is just checking your understanding that speed is scalar and velocity is a vector. So something is travelling at constant speed but changing velocity. Now that must be because it's changing direction. So they'd have the same magnitude all the way around. For example, this ball travelling around in the circle, let's say it's travelling at 10 meters per second, round and around and around and around. Well, yes, it'll have the constant speed as it's travelling around, because it's constantly changing direction as it's going around the circle, then its velocity is changing. Not the number on the velocity, but just the direction. So it'll always be 10 meters per second, but the velocity will be changing because it's a changing direction and velocity is a vector. With distance time graphs, you need to be very careful that the y-axis says distance and not velocity, and it'll always be over time. So a straight line at an angle like this one here shows that an object is moving at constant speed. A straight line that is horizontal shows that the object is stationary, and here again we would have another constant speed. This line here is much steeper than the third line over here, so it shows that it's moving at a faster speed. It's travelling more distance in a certain amount of time, and this one here a lot shallower gradient, which means it is travelling at a slower speed. You can calculate average speed on a motion graph using the following equation: speed equals distance over time, which is just rearranging that distance travelled equals speed times time equation. If you want to calculate the average speed in the first 10 seconds, you draw a line from 10 up to your graph and then across and read off your distance that it had travelled in 10 seconds. So we know here that within that first 10 seconds it's travelled 40 metres, so if we do 40 divided by 10 we'll get a speed of 4 metres per second. A curved line that gets steeper shows that an object is accelerating, and a curved line that gets shallower shows that an object is decelerating. If you're doing higher tier, you'll have to calculate the speed at a particular point on a distance time graph. For example, you might be asked to calculate the speed at 10 seconds. And in this case, you'd have to draw a tangent on the graph at 10 seconds. So here is our 10 seconds going up here, and that's why we've drawn a tangent at this point, which is a straight line as close to the graph as you can get it. You would then calculate the gradient of the tangent by doing the change in y divided by the change in x. So draw a triangle anywhere on that tangent, and we can calculate the x value, the y value, and we remember we always do the y divided by the x. So we do 17 divided by 7.5 to give us 2.3 meters per second. Velocity time graphs. With velocity time graphs, you need to check that the y-axis says velocity and not distance, because that's a different motion graph. With velocity time graphs, a straight line at an angle would show a constant acceleration. A flat line here would show a constant velocity because it's not moving above 40 meters per second in this case. A straight line going downwards at an angle would show constant deceleration. And then here we've got another straight line at a different velocity, so that again shows another constant velocity. You can calculate acceleration on a velocity time graph by calculating the gradient. So essentially we're using the equation acceleration is the change in velocity over time, where v is the final velocity and u is the initial velocity. You'll remember that one because U comes before V in the alphabet. So U is the starting one and V is the final one because that comes after. So if, for example, we said what is the acceleration in the first 10 seconds, we would calculate the gradient of this line here. So we'd have a look and we'd see that we have a velocity change from 0 to 40 in that 10 seconds. So 40, take away 0, so that's your final minus your initial, divided by 10, which is your time, should give us the acceleration. So acceleration in this case would be 4 meters per second squared, and have a look at the units for acceleration there. For higher T, you'll also have to calculate the acceleration at a particular point. So if we have a look at this graph here, where the acceleration is changing because it's a curved line rather than a straight line. If, for example, we were to ask for the acceleration at 10 seconds, we would draw a tangent at 10 seconds, determine our values for y and x from that tangent, and do the change in y divided by the change in x. So if we had a look at this, for example, we'd have 17 divided by 7.5 to calculate an acceleration of 2.3 meters per second squared. For higher T, you might actually have to calculate the distance travelled on a velocity time graph. And to do this, you calculate the area under a graph, because essentially you're using the equation distance travelled equals velocity multiplied by time. And if, for example, we're asked to calculate the distance travelled in the first 10 seconds, this would be the area of the graph we are looking at, but we need to calculate the area just under the graph, this shaded region here. So if we take some values from this graph, we're going to calculate the area. So if we do the area of the rectangle and then divide it by 2 to get the area of the triangle, that will be our easiest thing to do. So in the first 10 seconds, the velocity is 40 meters goes up to 40 meters per second. So if we do 40 times 10, which is equal to 400, and then we'll divide that by 2 because we've got ourselves a triangle, our distance travelled will be 200 meters. If we were calculating the distance travelled between 10 and 25 seconds, that would be this region here. You wouldn't need to divide by 2 because you're not looking at a triangle, you're looking at a rectangular section. Let's have a look at some acceleration equations then. We've got A equals V minus U over T, where acceleration is in meters per second squared, final velocity in meters per second, initial velocity in meters per second, and time in seconds. So you should remember that U becomes before V in the alphabet. So U is your initial or starting velocity because that comes first, and V is your final velocity because that comes afterwards. Let's have a look at this question. A dog was sat still when he heard someone at the gate. The dog reached the gate in 2 seconds, so that is going to be our time, and was travelling at 6 meters per second when he reached the gate. So this is our final velocity. Calculate the acceleration of the dog. Calculate A. So the other bit we need is U. We need the initial velocity, so you need to read the question very carefully again. It says a dog was sat still. So this here implies that the dog was stationary, therefore that is our starting velocity, which was 0. So then we can do 6 minus 0, so V minus U, divided by the time, which is 2, and our acceleration would be 3 meters per second squared. Then we've got another acceleration equation, which is V squared minus U squared equals 2AS. Again, acceleration, final velocity, initial velocity. S in this equation is distance. And let's have a look at this practice question. It says an aeroplane accelerated at 10 meters per second squared from 100 meters per second to 200 meters per second. Calculate the distance travelled by the plane while accelerating. So this time we're rearranging this equation to calculate S. You might have to rearrange the calculation to calculate any one of U, V, or A. So let's have a look at it then. 200 squared is our final velocity here. U is our initial velocity of 100 meters per second. So we square that, and then that is equal to 2, which is our constant in our equation, multiplied by acceleration of 10, multiplied by S. So if we simplify this, we're saying that 30,000 equals 20 times S, because those two make 30,000, those two make 20, and then rearranging it to 30,000 divided by 20 equals S. So S is equal to 15,000 meters. So let's consider the motion of this skydiver who's just jumped out of a plane. All objects falling towards the Earth will be accelerating at 9.8 meters per second squared. So this skydiver will have the force of weight accelerating him towards the Earth. And as he initially jumps out of the plane, he'll also have a very small air resistance acting in the opposite direction, which is shown by a smaller arrow. So here we've got a scenario where weight is larger than air resistance, and therefore the motion will be acceleration. So he's accelerating towards the Earth. And then as speed increases, so as he accelerates, then air resistance will also increase until you get to a point where the air resistance will balance out the weight, shown by the same size arrows here. And in this case, he will be not accelerating anymore, but he would have reached a constant speed. And when he's falling, because he's falling through a fluid, we call this constant speed a terminal velocity. So fluids are liquids and airs. And air, if you are falling through a liquid or a gas like air, then you are said to reach a terminal velocity, which is your final velocity. You can't go any faster than that at the point that your weight matches the air resistance, is balanced by the air resistance. So then the parachutist will deploy a parachute, and at this point there is a much larger air resistance and a smaller weight, which will cause a deceleration. And then finally, the air resistance and the weight will balance each other out again, because he'll slow down and air resistance will decrease. So those two will balance out again, and he will reach a new constant speed, and therefore, because he's falling, a new terminal velocity. So for separate science, you'll also need to link this into a velocity time graph, so looking at how the shape of the graph explains the motion. So if we look at the skydiver again, at this first point we could be sketching acceleration until he reaches his first terminal velocity. So here at this point he had unbalanced forces and was accelerating, and then at this point he reached balanced forces and was reaching a terminal velocity here of 60 meters per second. Then after his parachute opens at this point here, he would have a large deceleration until he reached his final velocity. Again, another terminal velocity here, because the forces become balanced again. So relating the force diagrams to motion graphs will be something that you might have to do. Momentum. Momentum is equal to mass times velocity. Momentum is measured in kilogram meters per second, which is the unit for mass multiplied by the unit for velocity. So you just write the two next to each other. Mass is measured in kilograms and velocity is measured in meters per second. The conservation of momentum says that the total momentum before an event is equal to the total momentum after the event. Now let's look through some worked examples for momentum calculations. The first one that we'll do is a collision. In this question says stone 1 slides to the right and hits the stationary stone. After the collision, it kept moving in the same direction at 0.5 meters per second. Calculate the speed with which stone 2 moves to the right. So initially the speed of this stone 1 was 2 meters per second and its mass is 20 kilograms. That was moving to the right and it hits this stationary stone, stone 2, that is stationary. So this tells us that it has a speed of 0 meters per second and it also has a mass of 20 kilograms. So the momentum of stone 1 before is 20 multiplied by 2 because mass times velocity is momentum. So the momentum before of stone 1 is 40 kilogram meters per second. And the momentum before of stone 2 is 20 times 0, which is 0 kilograms meters per second. So if we add those two together, the total momentum before would be 40 plus 0, which is 40 kilogram meters per second. So all we've done is before the collision, we've worked out the momentum of stone 1, that was 40, the momentum of stone 2, that was 0. Add them together and we get the total momentum of the whole system before the collision. So the total momentum after, because of conservation of momentum, must also equal 40 kilograms meters per second. That's not given to us, that's just through our knowledge of the conservation of momentum, that total momentum before is equal to total momentum after. So now we can calculate the momentum of stone 1 after, because in the question it told us that it kept moving in the same direction, but this time at 0.5 meters per second. It's got the same mass, so it's still a 20 kilogram stone. So this time its momentum is 0.5 times 20. So now its momentum is 10 kilograms meters per second. So that's momentum of stone 1. So if we know the momentum afterwards should be equal to 40, we know that 10 kilograms meters per second of that is taken up by stone 1. So we know that momentum of stone 2 must be 30 kilogram meters per second because 40 minus 10 is equal to 30 kilogram meters per second. So stone 2, we can calculate the speed or velocity with which it moves to the right, because momentum equals mass times velocity rearranged will give us momentum divided by mass equals velocity. So if we take the momentum of 30, divide by the mass of the stone, which is also 20, this tells us that stone 2 moved away with a velocity of 1.5 meters per second. Now let's look at an explosion example. This one says a cannonball with a mass of 5 kilograms is fired from a 100 kilogram cannon at a speed of 150 meters per second. And the question says calculate the velocity of the cannon as it recoils in the opposite direction. So when the cannonball is fired out, that will go in this direction, and the cannon itself will recoil in the reverse direction. So we've got the total momentum before is 0 kilogram meters per second. And that is because before the explosion, everything is stationary. The cannon is stationary and the cannonball inside is stationary. So nice easy one, we know the momentum before is going to be 0. That means the momentum afterwards must also equal 0 because the momentum is conserved. So we can work out the momentum of the ball from the information in the question, because we have been told it has a mass of 5 kilograms and it travels with the speed of 150 meters per second. So mass times velocity is equal to 750 kilograms meters per second. And you'll notice the plus here, because we're talking about velocities. I have decided that going right is a plus direction, and going in the opposite direction we'll assign that a minus. So the ball is moving to the right, so we're going to describe it as plus 750 kilograms meters per second, and the recoil of the cannon will be a minus number. So the momentum of the cannon afterwards is, we know, must be minus 750. And we know that because total momentum afterwards must be equal to 0 because of the conservation of momentum. And if the ball has gone forward plus 750 kilogram meters per second, then to get to 0, the momentum of the cannon afterwards must be minus 750, because if you add those two together, you get a total momentum afterwards of 0 kilogram meters per second. Okay, so that's how you get to that bit. So we know the momentum of the cannon afterwards is minus 750 kilogram meters per second. And if we rearrange momentum equation, momentum divided by mass is the velocity. In the question, they've told us the mass of the cannon is 100 kilograms. So if we rearrange that, we will get minus 750 divided by 100 to give us a velocity of minus 7.5 meters per second. And again, the minus is there just because velocity is a vector, so it shows us or gives us an indication of the direction that that cannon is moving in.
Okay, so applying the rate of change of momentum equation. Crumple zones in a car, airbags in a car, seatbelts in a car, gym crash mats, cycle helmets, playground surfaces, all of these things keep people safe in an accident, and they all work in the same way. So all of these safety features, they reduce the forces on a person, and it's those forces that will hurt someone, that will injure someone. And how do they do that? Well, they reduce the rate of change of momentum. So if we need a reminder of what momentum is a measure of your mass times your velocity. So when you're in an accident, when you're stopping, you hit a crash mat or you hit an airbag in a car, you go from a high speed to a low speed. And that can't be changed. Inevitably you're going to have to go from that high speed to the low speed. And that is the same as saying you're going to go from a high momentum to a low momentum. Now we can't change that change in momentum. You're going to have to go from high to low no matter what. But if we can change the rate of change of that momentum, as in we can make that rate of change happen over a longer period of time, it's going to keep you safer. So all of these safety devices, they all make going from a high momentum, as in fast, to a low momentum, as in moving slowly, they make that occur over a longer period of time. In other words, they make you stop slowly instead of stopping suddenly. It makes a lot more sense when it's said like that. So how can we prove then that to reduce the forces on a person in a crash, we need to increase the time they stop over? How do we know that? Well, F equals ma tells us that in order to reduce the forces, if I want to reduce that number there, I have to reduce the acceleration. And that's because in an accident, we can't suddenly become lighter, so I can't change the mass of a person in an accident. I can only change their deceleration. So how do I reduce their deceleration in an accident then? Well, if we have a look at a equals v minus u over t, this tells us that to reduce the acceleration, well, we can't change the final speed and start speed. That's going to be from very fast to stopped. We can't change the speed change in an accident, but we can change the length of time that speed change occurs over. So to reduce the deceleration, we have to increase the time taken to stop. Now that leads us on to our equation, the rate of change of momentum equation. So when we combine F equals ma and we swap a for v minus u over t, when we combine those two things, we're left with F equals mass times the change in speed divided by the time that occurs over. And that is the rate of change of momentum equation. I would recommend in a question, just as I've shown you before, underline the numbers in the equation, and then so if you've got maybe 15 kg and 2.0 seconds, just underline those things and write above them what they are. This is an equation you get given, so on the equation sheet you can pick it out, but if you've already written down those symbols for it, that'll make it a lot easier for you to pick out.
Forces and elasticity. To squash or stretch a stationary object, you need to apply two forces that push or pull an object. So the other word for squash is to compress. So you need two forces, because otherwise if you just had one force applying against the object, that would cause the object to accelerate in the direction of force, because of force equals mass times acceleration. So if you just had one force, that object would accelerate in the direction of the force. However, if you have two forces, that can then, in this case that we're going to do, cause the object to compress, or equally, if they were pulling, you could cause the object to stretch. To stretch a spring, you need to apply two forces that pull either end of the spring. So, for example, you could have it on a clamp here, and you could add some weights to that, so you'd have the force of weight acting downwards, and then a tension force acting in the opposite direction. That is two forces, therefore applying on the string and allowing it to stretch. So there are two types of objects. There are elastic objects. Those are objects that return to their original shape after being stretched. So if you think of a spring, once you remove a weight, as long as it's not too much of a force that has stretched it, if you let go of that weight, take it off, it will return to its original shape. And in that form, it is elastic, and we could say it has been elastically deformed. So when you take off the forces that are being applied to that spring, it will return to its original shape. Inelastic is the opposite. So inelastic objects are the opposite to elastic objects. They don't return to their original shape after being stretched. So again, we would say an object in this case has been inelastically deformed, and there's no chance of getting that to return to its original shape. Hooke's law: some elastic objects, importantly, obey, like springs, obey Hooke's law. Hooke's law states that when you double the force applied to an object, the extension of the object also doubles. And there's an equation that comes into play here, which is force is equal to spring constant times extension. Force is measured in newtons, spring constant is measured in newtons per metre, and extension is measured in metres. So force is directly proportional to extension in elastic objects. So if we were to plot force against extension, this time I've got it in centimetres, but you could also have converted it to metres. When an object is obeying Hooke's law, a graph of force against extension will show a straight line that goes through zero. Remember, this relationship is called directly proportional. Any straight line through zero is directly proportional. If the object is overstretched, it will lose its elastic properties and the graph curves off. And this point here, we'd call its elastic limit, or limit of proportionality, because that is the point that it is not proportional anymore. So here is its limit of proportionality. And at this point, it's gone beyond its elastic limit and no longer obeys Hooke's law. Work is done when a force stretches or compresses an object. And in this case, we remember we're talking about two forces needing to stretch or compress objects. An energy is transferred to the elastic potential energy store of the object. So we know that work done and energy are both measured in joules, because work done is the same as energy transferred. So when you compress or stretch an elastic object, it will transfer energy to the elastic potential energy store. And this equation links our factors. We have elastic potential energy is equal to 0.5, which is a constant, that stays the same, multiplied by spring constant, multiplied by extension squared. And we measure elastic potential energy in joules, spring constant in newtons per metre, and extension in metres. pressure, and pressure differences in fluids.
Okay, so fluid pressure. Pressure increases with depth. So if you had a can with holes in it at different depths, you'd see that the pressure would be highest at the bottom and hence the water would be coming out further. So as depth increases, so does the number of particles above that point. So as you go down, there are more particles above that point. The weight of these particles adds to the total pressure. Okay, now there's an equation for pressure at depth. So now pressure equals rho g times h, rho being the density of the liquid, g being the strength of gravity, and h being the height of the container. So fluid pressure, so the pressure inside a liquid, it doesn't depend on the shape, doesn't depend on the total mass of the liquid, and doesn't depend on the surface area of the liquid. So you can see in these three different shaped objects, the pressure at this depth just here would be exactly the same in all of them. Okay, so pressure equals rho gh. Okay, now atmospheric pressure. So if we look at a little man up a mountain or a little man at the bottom of a mountain, at higher altitudes, air pressure is less. And this diagram helps us to see why that is. So the higher the altitude, the higher up you are, if you're up here, the higher the altitude, the less air there is above you, the fewer air particles there are above, so they press down with a smaller force. And the further down you are, the more particles there are above, so they're pressing down more, meaning that all the particles are closer together because there's a bigger force pushing on all of them. And if we were to draw a graph of air pressure against altitude, against height above the ground, we would see that the pressure is very low when we're really high up in the atmosphere, and you can see it steadily increases as you get closer towards the ground. Okay, so upthrust. So this is to do with things floating. So why do things float then? If we have a look here at an apple floating in some water, well, the apple is displacing some water. So the apple is pushing this amount of water out of the way. The size of the upthrust force is the same as the force of the weight of the water that has been displaced. So you'll have pushed some water out of the way with the apple, and the weight of that water being pushed out of the way is the same as the size of the upthrust force. So that's why ships need a large volume below the water so that they can carry lots of heavy goods, because the bigger the volume of water they push out of the way, the more mass and more weight of the boat they can carry. Okay, so how can we explain this upthrust force? So why does a cube of ice float upwards when in water? So if we take our cube of ice and we have it deep underneath the water, well, what do these arrows tell us? What are these arrows from? So pressure increases with depth, as we saw earlier. So the further down the ice cube is, the more the pressure is. But even on the edges of the ice cube, at the top of the ice cube, there will be less pressure than there is at the bottom. So the base of the object down here will feel a higher water pressure than the top, meaning that overall there'll be a resultant force upwards, and this is called upthrust. So down the bottom there's more force, there's more pressure acting on it than there is from the top. So overall we're going to have an unbalanced force upwards. And the upthrust is equal again to the weight of the water displaced.
Waves in air, fluids and solids.
So we've got transverse waves and longitudinal waves. Now I'm sure all of you have seen these on a slinky, so I've included these pictures here just for a graphic. So transverse waves are where the vibrations are at 90 degrees to the direction of energy transfer. So let's have a look here. Transverse wave, he's moving his hand side to side. As his hand moves side to side, the slinky shakes from side to side, but the direction of energy is going forwards, okay, away from the person who's shaking their hands. Okay, and longitudinal waves are with the different type of vibrations. They have vibrations which are parallel to the direction of energy transfer. So this person is moving their hand in the direction of the wave, and the direction of the energy is still going away from the person as they move their hands backwards and forwards. And you can see here that what you see move down the spring are areas where the spring are squidged up, and areas where the spring is spread out. Okay, and we give those scientific names. We can say that this is an area of expansion, so they are far apart, and this is an area where they are compressed, so compression. Okay, and expansion or rarefaction, we sometimes call that. Now, you need to know examples for both of these. Light and electromagnetic waves both travel as transverse waves. Sound travels as a longitudinal wave. So our air particles in between our ears and our vocal cords are doing this sort of effect here, where you get areas where they're spread out and areas where they're closer together. Okay, so which could be shown on a slinky as well. Okay, so having a look at these diagrams in a bit more detail then. So we've got a wavelength of this transverse wave. One wavelength goes from one peak to the next peak. And here's our peak there. Down at the bottom we've got a trough because of that shape U. We've got our peak up here. Now wavelengths may not only be from peak to peak or trough to trough. Okay, they could also be from a 0 point to the next 0 point after a full wave. So a full wave includes an up and a down part. Okay, so with these waves here, and in fact with both types of waves, frequency is a really important idea. Frequency refers to how many waves go past per second. Okay, so time period then, what's time period? Time period is how long one wave takes to pass. Okay, now these two things are clearly related. If a wave goes by in a short amount of time, you're going to have a high frequency. And they're related using this equation here. T, for time period, equals 1 over the frequency. Okay, so the higher the frequency, the bigger the number for the frequency, the smaller the time period, the shorter the length of time of wave. Okay, and here are the units for what they're measured in. Now in our longitudinal wave, so our examples were sound for that one, we've got an area of rarefaction where they're spread out. We've got an area of compression here where they're squidged up. Okay, now one wavelength then. One wavelength is going to be from the back of the compression to the front of the compression, or it could equally be from the middle of the compression to the middle of the compression, or from the end of the compression to the end of the compression. It has to be one full wave, and a full wave, because it has to include both a peak and a trough, has to include one compression and the rarefaction as well. So that there would be a badly drawn wave. Maybe that's a bit better there. Okay, now this very important wave equation here, V equals F times lambda. If ever there's an equation in physics that you need to know, it's this one. It comes up in every exam paper I've ever seen. So V equals F times lambda. So what do the V, the F and the lambda stand for? V is wave velocity, the speed of the wave. F is the frequency of the wave we've come across just over here, and wavelength is the length of from one compression to the next compression, or from a 0 point to a 0 point, that wavelength there. So the wavelength, the length of the wave is related, you times that by the frequency to find how quickly the wave's going past. This has to be one of the most important equations in physics. There are 5 examples of practicals that you need to know about for measuring wave speed. 3 of them all use the wave equation, which is V equals F lambda, as you can see down here, and the 2 on the next slide use the speed equals distance over time equation to work them out. Now, you would have seen all of these in class, but it's just a quick whistle-stop tour of how to, of just briefly how these work. So this is an example where we've got a signal generator, a speaker, and 2 microphones. And we've got an oscilloscope that shows the shape of the wave on the oscilloscope. Now you start off with both microphones starting together at the same distance, so you would have the other one just above it as well, so they're the same distance from the speaker, that same distance there. Then you would gradually move the second microphone away until the wave that appeared on the oscilloscope had moved one full wavelength along. And when it's moved one full wavelength along, the distance between the 2 microphones tells you, therefore, that is 1 wavelength, lambda. The frequency you would read from the signal generator, along with all of these, they've all got signal generators on. Then you would use that equation. So if you get an exam question that asks you to explain any of these methods, you have to give the equation to say what you would do with the values you take from the practical. Okay, so for these practicals, you need to use the speed, distance, time equation And this is what the speed distance time equation looks for your GCSEs. Velocity, speed, equals displacement, which is an s, divided by t. So it's velocity, speed, equals distance, displacement, divided by time. Okay, so v equals s over t. Not to be confused with in year 7 when we would have used speed as s and we would have used d for distance. Not to be, it's the same equation but with different symbols now. So here we've got a laptop hooked up to 2 microphones. The 2 microphones simply just record when the noise goes past. So the laptop is hooked up, designed to tell us when the noise goes past the first one and then the time to get it past the second one. So the microphones record the time for the waves to pass. You need to measure the distance between the microphones. Okay, that'll tell you the distance, and then on the computer that'll tell you the time on the computer. You can use speed equals distance over time. Okay, the next one is about the echo method. So here we've got a guy firing a cannonball. Now that noise is going to go off to the wall. It's going to bounce back from the wall and it's going to come back to him. So use a stopwatch to record the time for the sound to travel to the wall and back. You need to measure the distance to the wall and back. Don't forget about that bit. Then use speed equals distance over time. Be prepared in the exams. I've seen examiners ask, they've deliberately not times the distance by 2, or they've deliberately only given the time for the sound to reach there. So keep an eye over that. That's got to go there and back again. So when light hits a surface, it can be reflected, transmitted, or absorbed in different amounts. So here we have some sunlight hitting a window here. We can see that some of it is absorbed into warming the glass of the window. Some of it is transmitted through, and some of the energy is also reflected as well. Now, reflection happens in 3 different ways. So if light hits a surface, for example, if it hits a wall, we would say it has diffuse reflection. We can see light being reflected from the wall, but we can't see a picture coming from the wall. And that's because diffuse reflection is where the light is scattered and scatters in all different directions. So we don't end up with a picture, but we can still see the wall because light is being reflected from it. Now, specular reflection is for smooth surfaces. So specular reflection is where the light hits and leaves at the same angle. And this would be, for example, a mirror where you can see an image clearly in the mirror, or maybe reflected from a window if you're at the right angle. Now, the law of reflection states that the angle of incidence equals the angle of reflection. So this angle of incidence, to start off with, we have to draw our imaginary line, our normal, and we draw that at 90 degrees to the wall, to the surface. Our angle of incidence is between the incident ray, the ray coming in, and the normal, and our angle of reflection is between the normal and the ray. Okay, so really important to remember to draw that normal, and that our angles are measured from that normal. Okay, so what is ultrasound then? So ultrasound is sound or vibrations above human hearing, or above 20,000 Hertz. That's the number you need to know. So how does ultrasound imaging work? Well, there is a partial reflection at each interface. So ultrasound is what they might use with unborn babies to look at them. There's a partial reflection at each interface. You shine this ultrasound in. I say shine, really send it in, transmit it in. At every boundary, for example, between skin and bone or between skin and fat, there'll be a little bit of reflection and some transmission. So some passes through, a little bit gets reflected back each time. The reflected pulse is detected and used to work out the time delay between layers. So if you've got multiple layers, each time the light goes in, there's a little bit of reflection, and the time delay from each reflection can help you to work out the distance between the layers. So here's an example of a picture you may see in the exam. So here is something being emitted onto the skin, an ultrasound pulse being emitted onto the skin. And this is the first partial reflection from the front of the bone. This is the second partial reflection from the back of the bone. These could be 2 tiny little partial reflections as it enters the bone marrow on the inside of the bone. And in the exam question, they'd be likely to tell you maybe what the speed is of ultrasound in that medium, in that flesh or bone, and the time delay of that as it passes through it, letting you work out the distance s between the layers, so you can work out how far away an object is, for example. Okay, so it gives you fuzzy images, but it is really safe. It's much safer than using X-rays. If you think about imaging fetuses, we don't want to expose those to cancer-causing radiation. So it's used for a few things. Used for destroying kidney stones. They'll shake the kidney stones to pieces, and it'll pass out of the small pieces will pass out in urine. Can be used for cleaning maybe antique watches, a very delicate material, detecting flaws or cracks inside building materials. For example, steel girders used for skyscrapers. Got to make sure there's no faults in those before they're used.
So further to ultrasound waves being used to study the structure of objects, seismic waves are studied to investigate the structure of the Earth. And earthquakes are the things that produce seismic waves. And seismometers are placed all around the Earth to detect these waves. And there are two seismic waves. There are P waves, which are longitudinal waves, and there are S waves, which are transverse waves. P waves are longitudinal, they travel through solids and liquids, and they travel faster than S waves. And S waves are transverse, they can't travel through liquids or gases, and they travel much slower than S waves. So the properties of these have helped us investigate the structure of the Earth. So let's say, for example, that an earthquake happened at this point here on Earth, if we're using this as our Earth model. The S waves would be shown to travel through the mantle of the Earth, both sides like this as the waves are generated, and seismometers around the Earth, for example here and here and here, would detect these S waves, but because S waves can't travel through liquid, then they can't travel through this liquid layer here, the outer core, and therefore you won't detect S waves around this area of the Earth if this was the original place of the earthquake. So they were looking at these S waves, and from that they surmised that there must be a layer of the Earth that is liquid, and this is the outer core. So that would be the pattern of the S waves, and the P waves, also generated by the earthquake, would also travel through the mantle, because they can travel through, well, the mantle's nearly solid, very nearly solid, slight movement on it, but they can travel through the mantle, and they also can travel through the liquid outer core. So you will see the waves going into this ring here, but they will refract when they get into that inner liquid ring. So they won't go in a straight line, you'll see them refracting and bending as they come down. They can also travel through the solid inner core, and then again through the liquid outer core, and again back into the mantle. And as they go through different mediums, they'll be refracting as they're changing speed. So with these S waves, there will be with these P waves, there will be a smaller region on the Earth where seismometers would not detect any activity, so there'd be nothing detected in this region, but it can travel through the liquid outer core as well as the solid inner core. And these patterns of S waves and P waves help them understand which parts of the Earth structure are liquid and which are solid. And studying these waves helps to the current understanding of the structure of the Earth, where the inner core is solid with a liquid outer core, a mantle which is mostly solid with some slight movement, and then the crust around the outside. So remembering that S waves are transverse, P waves are longitudinal, and it is the S waves that can't travel through liquids, and that helped them understand which parts of the inside of the Earth were liquid, which were solid, and also the refraction, the changing of speeds as the waves go through, helped them again understand which parts were liquid and which parts were solid by looking at where the seismometers detected those P waves. Solar system, stability of orbital motions and satellites.
So the solar system. Within our solar system, there's one star, the Sun, plus our 8 planets and a few dwarf planets that orbit around the Sun. Now, natural satellites, they're the moons that orbit planets. They're also part of the solar system, and there's hundreds of moons in our solar system. Our solar system is a small part of the Milky Way galaxy, so around 100 billion stars in our Milky Way galaxy. Now, the Sun was originally formed from a cloud of gas and dust called a planetary nebula, which was pulled together by gravitational attraction. And this leads us nicely onto our stellar evolution, so our life cycle of stars. Now, you get 3 different types of stars, which have got 3 different types of endings. Light stars, which are up to about 8 times the mass of our Sun, medium stars, and massive stars. So let's have a look at what all stars start off as then. So the force of gravity will attract dust and gas in a vast region of space full of dust and gas. Eventually, as they start to fall down, the force of friction will warm them up, and they get so hot as they fall down that they will actually start doing nuclear fusion. And when they do nuclear fusion, they'll basically turn on as a light. Now, once they've lit up, once they're doing nuclear fusion, they'll be converting hydrogen into helium in nuclear fusion. They become what we call a main sequence star. So our star at the moment is a main sequence star. And every star that lives will go through this phase, even if it's just briefly. So we're going to start off with the sequence of lightest stars. So the lightest star, like our Sun, would go protostar, main sequence star. Now, as it starts to use up its fuel, and it runs out of fuel here, it's going to expand rapidly into a red giant. And once it's gone into a red giant, it's going to carry on burning the rest of its fuel above helium in the periodic table. And once it's used up all of its fuel, it's going to start to shrink back down again into a white dwarf. So the force of gravity would pull that back into a slightly smaller size. And as it keeps cooling down, it keeps on using the last of its fuel. Eventually, it's just going to fade away into what we call a black dwarf, where we can't see it anymore because it doesn't give out light. So that's the pathway of our lightest stars, like our star. Now, we have other stars which are much more massive than ours. Now, these ones, after being a main sequence star, after burning up most of their hydrogen into helium, the heavy mass stars would then form a red supergiant. So, a giant again, but this time a supergiant, because they're very special. And these ones, once they've used up the last of their fuel, they will collapse inwards really rapidly. They collapse inwards so rapidly that when they collapse, they explode outwards in one of the largest explosions in the universe, called a supernova. So the explosion of a star or a dying star. Now, during the supernova is where they will make elements which are heavier than iron in the periodic table. So all of our golds and uraniums and silvers, they'll all be made in a supernova explosion. Now, after the supernova explosion, and that's ejected lots of material into space, lots of those elements into space, what will be left behind is what we call a neutron star, which is made of neutrons and is very, very dense. Now, the most dense stars, the heaviest stars, about 10 times the mass of our Sun, well, they will actually go through the neutron star phase straight into a black hole. And a black hole is where mass itself has collapsed in on itself to have no size, and hence they can't be seen because they've got no size. But they're still incredibly heavy with a very strong gravitational force. Okay, so orbital motion. So orbital motion is the science of objects rotating around a fixed point. Now, velocity is a vector quantity, and so it includes both the magnitude of speed, like the size of the speed, and it also includes the direction as well. So when something is in circular motion, the velocity is constantly changing because the direction is changing. So even though the speed can be constant, the direction is changing, so we can say velocity is changing. Now, if velocity is changing, that's the same as saying something is accelerating. Its velocity is changing, so it's accelerating. So we've got an object here which is being pulled towards the centre. Let's say it's a concher on a string. The force will always be towards the centre of the circle. If you were to snip the rope at any one point, the object will carry on at a tangent to the circle there and will carry on going at 90 degrees to the direction of the force that was pulling it in. Now, the example of uniform circular motion or orbital motion that they use in the exam board is planets orbiting stars. So if a planet or a moon is in a stable orbit, stable meaning that the distance of the object from the planet is staying the same, if the speed changes, the orbit radius has to change too. So if you make the radius smaller, or you make it's the same as making the speed faster. So something will orbit a planet much faster at a smaller radius. The further away from the planet it is, the slower the speed it can have. And this is because the force of gravity is stronger near the object. So because the force is stronger, it'll make it rotate quicker.
Redshift.
Okay, so redshift then, evidence for an expanding universe. So how do we know that the universe is expanding? Well, when we look up at distant galaxies in the sky, the light is more red than expected. The only way to explain this red light is because the galaxies are moving away from us. So the redshift effect is, the further away a galaxy is, the longer the wavelength of light we receive. The further away the galaxies, the faster they're moving and the bigger the observed increase in wavelength. This effect provides evidence that space itself, the universe, is expanding and supports the Big Bang theory that states that all matter started in one place. So let's have a look in a bit more detail then. So when an object moves away from you, if we've got a star here, a galaxy rather, which is moving to the right, if you've got someone watching it moving away, as in the galaxy is receding, then those light waves which are given out become stretched because the galaxy itself is moving. Now, if for example, you had a galaxy moving towards you, you would see that the light from that becomes squashed up because that object is moving towards you as it's giving out the waves. So the light waves will become squashed, we call that blue shift, and if the galaxy is moving away from you, the light waves become stretched, meaning redshift. So here's an example of the evidence that, a simplified version of the evidence that we use to prove that the universe is expanding. So if we've got a star which is at a fixed distance from us, we can see all the colours of the rainbow that come out of that star. And the star has what we call absorption lines on it. These are lines where those wavelengths, those particular frequencies of light are being absorbed by the elements in the star. So hydrogen, helium, any other elements in there. And they will absorb specific frequencies of light that comes out of the star. So these are called absorption lines. And those absorption lines are due to the elements in it. So we know what those elements are because we can recreate them on Earth. So if the star is at a fixed position, we get kind of a yellowy light coming out of it. Now, when we look at a object which is moving away from the Earth, and we have a look at those, the absorption lines are moved slightly to the red end, ever so slightly to the red end. So these are further away, and so this tells us that the object is moving away from us. Okay, and if we've got the galaxy is moving towards us, then we see that the star is blue shifted. Evidence for the expanding universe. How does this prove it? How do these absorption lines prove it? Well, light from distant galaxies is more red than expected. The light is shifted to the red end of the spectrum. Here's our colour spectrum. The light has been shifted over, these absorption lines have been shifted over to the redder end of the spectrum. The further the galaxy is away from us, the more redshifted it is. So those absorption lines are moved even further away. If we rewind the positions of all the galaxies in the universe that we can see, and we were to rewind them all, because we can see they're all accelerating away from us, if we were to just rewind all of that, we see that they start off in one place.